Hello and welcome back once again. So, we have discussed about grain refinement as a technique for strengthening, and we have also had a detailed discussion on the Hall-Page relation with regard to grain refinement strengthening. Okay? And we have learned about different dislocation models or theories which explain the Hall-Page relationship. Alright, so this will be our next topic, grain refinement methods. There are different ways, different techniques by which the grain size can be refined. It can be started right in the beginning when the material is processed. So you can do it during the melting operation itself. And in this case, you need to consider the solidification behavior of the material as to what can be done to this so that it is modified in a manner which will lead to a fine grain size. Right, so you need to do something during the melting operation before the casting is done, so that you provide some driving force for the grains to be refined or broken down into smaller sizes. Right. So one of the ways by which that can be done is through heterogeneous nucleation. Because the solidification phenomenon is all about nucleation and growth of the solid from the liquid phase. And if you can provide some heterogeneous nucleation sites, it will basically increase the nucleation rate, which will lead to a finer grain size. So in order to understand as to why that happens or how does the heterogeneous nucleation help, you need to understand the difference between homogeneous and heterogeneous nucleation. Homogeneous nucleation, as the name itself suggests, it occurs uniformly across the material. And there is no preferential sites for the nucleus to form. So the homogeneous nucleation occurs without the aid of any surface or any defects. And in this case, the surface energy will also play a role as a new surface is created. So let us talk about this first, then we'll come back to the heterogeneous case and see how it helps in refining the grain size. So let us restrict ourselves to this solidification phenomena, that is this transformation from liquid to solid. And for this, let us consider this diagram where the first particle of the solid is forming from the liquid. So let's say this is the solid which has formed. So above this you have all liquid. It forms unaided by any surface or defects. As the solid particles form, an interface between the solid and the liquid is created. And therefore, surface energy or interfacial energy is involved here. Right, so this is the first particle of the solid which forms, and this is known as the nucleus when it attains a critical size. Okay, so only when it attains that particular size, it will grow into the solid. If it is below that critical size, then it will be known as an embryo, which is not stable. Okay, so it has to reach that critical size for the nucleus to grow into a solid. So this free energy change that you have here for this particular transformation from liquid to solid, that has two components. One is the surface energy and another is the volume free energy. Okay, that is shown over here in this particular diagram. This part that you see on the upper side, that is the surface energy contribution, and on the lower side you have the volume free energy contribution to this delta G. Okay, and delta GV is the specific volume energy change, that is free energy change per unit volume, right? So if you consider this tiny particle of the solid as a spherical particle, then the surface area would be 4 pi r square, and if gamma be the specific surface energy, that is surface energy per unit area, then the surface area contribution to the free energy change is this 4 pi r square gamma, and the volume free energy contribution is this, where 4 by 3 pi r cube is the volume of that spherical particle, right? And this is the summation of these two, the solid line that you see. Okay, so the maximum that you see over here, that is the size that the particle has to reach for it to be called as a nucleus, which can grow into the solid, right? If it is below this critical size R star, then it will be an embryo, and for it to grow as a nucleus and develop into the solid, it has to reach this critical size. Then only it will be called as a nucleus. Okay. So if you now take up these contributions, this is what you would get. right? As I said, it has two contributions, the volume free energy and the surface energy, right? And since the critical size occurs at the maximum, as you could see, right? If you take the derivative of this delta G with respect to the size, then at this point it will be 0, right? So that's what is shown over here. D delta G by dr is equal to 0, and this is the derivative, 4 pi square delta G plus 8 pi r gamma. That is, if you simply differentiate equation 1 with respect to r, this is what you get. And from here you can derive r star as this minus 2 gamma by delta GV, that is the critical size or the critical radius of the nucleus. And you can also derive the critical free energy change for the nucleus to form. And it will be given by this particular equation over here, right? So this is homogeneous nucleation, where the whole process is mainly controlled by the surface energies, okay? So as long as you have a driving force for this surface to be created, this will continue. So what is different in heterogeneous nucleation? In the heterogeneous nucleation, you have some preferential sites for the nucleus to form, right? It is not going to be uniform anymore, as you have seen for the homogeneous case, right? So the nucleus will tend to form at some preferred sites, such as the mold wall, when you are pouring the liquid metal into the mold. Inclusions, if they are present in the liquid metal as suspended particles. Grain boundaries, right? So these are the sites which can act as the preferred or preferential sites for the first nucleus to form, right? And that is why this is known as heterogeneous nucleation, because now the nuclei will form heterogeneously at such sites rather than forming homogeneously. As shown in this diagram, where theta is the contact angle, and now if you consider this into the free energy change, you would see this additional term in the form of theta will come. Okay, so in case of the homogeneous nucleation, critical free energy change is given by the surface energy and the volume free energy change. But in case of the heterogeneous nucleation, now there will be an additional term in the form of the contact angle. Right? So from here you can easily see that for small contact angles, delta G heterogeneous is going to be much smaller compared to delta G homogeneous, right? And as a result of that, when you have heterogeneous nucleation sites, more number of nuclei can easily form compared to the homogeneous case, right? So that is how you get a higher nucleation rate also in case of the heterogeneous nucleation. and higher the nucleation rate, lower will be the grain size, and that is how the heterogeneous nucleation leads to a finer grain size in the solidified material. Okay. Yeah, so this is all about the nucleation rate. It all boils down to the nucleation rate now. You have to have a higher nucleation rate which can actually beat the growth rate, because now the nucleus is also growing. So which one will prevail, that would decide the grain size. If the nucleation rate prevails over growth rate, then it will be a finer grain size. And if the growth rate prevails, then it will be coarse. So for a high nucleation rate, you also need to form more number of nuclei in a given time, right? So therefore, you need heterogeneous nucleation sites or preferential sites for the nucleus to form, right? So that's why heterogeneous nucleation will give you a finer grain size. On the other hand, if it is only through homogeneous nucleation, you may or may not get a fine-grained material at the end of the solidification process. Now the question would be how to create this heterogeneous sites. Okay, you do not know what is there in the liquid metal. It is all melted now, everything is in liquid state. So inside what is there we do not know, right? But at the same time we have to make sure that we have certain things which can act as preferential nucleation sites. Inclusions are not the answer for that, because many times this kind of inclusions, if they are present, they can be detrimental for many of the properties such as ductility, fracture toughness, and so on. Right? So we cannot really rely on these inherent inclusions which may be there due to some reason. So therefore, externally we need to create some nucleation sites by having suspended particles into the melt. So here we are basically adding some grain refiners into the liquid metal, and these grain refiners will actually provide you some solid suspended particles in the melt, and these will act as the preferential or the heterogeneous nucleation sites. So we have to talk about this in little more detail, but let me briefly tell you today as to what is done to generate these solid suspended particles in the melt. So basically what is done is, you have to have a metal which can remain solid at the liquidous temperature of the material that we are attempting to grain refine. Let's say we are talking about this aluminum alloys, which is the material in question for this particular course. We can add a material like titanium for generating these solid suspended particles. Okay, so this titanium surface will now act as the heterogeneous nucleation site, because these kind of particles can be still solid even at the melting point of aluminium. Okay, but this is not really metallic titanium that you are going to have inside the melt. It is the intermetallic which will form between aluminum and titanium, and these intermetallic particles will actually act as the heterogeneous sites. And how do you do this? You basically use this aluminum titanium master alloys, because you cannot add titanium just like that into the liquid aluminum. Okay, rather you already have this titanium in aluminum in the form of these master alloys, and then you can take a very small amount of this, a minor amount of this master alloy having a certain percentage of titanium is enough as a grain refiner. Right? So this master alloy will provide these intermetallic particles having a much higher melting point. So they will be still solid in the melting point of aluminum. So they will be in the form of solid suspended particles inside the melt and will act as the heterogeneous nucleation sites and increase the nucleation rate. Okay, so that is how, with the help of adding such grain refiners, you can actually increase the rate of nucleation, and as you solidify the metal, the microstructure will be fine grained. Okay, so this is a topic that we are going to discuss in more detail, as I said, but let me also tell you there are other techniques also as far as the melting and casting route of grain refinement is concerned. And those are basically application of some mechanical force through which you can actually refine the grain size. Mechanical force or agitation created into the liquid metal. Okay. So once you melt the material, you provide some mechanical force to agitate the melt. What that will essentially do is it will break down the dendrites which are forming as you cool it down. And now these broken pieces of dendrites will act as the nucleation sites and increase the nucleation rate. And there are different ways by which you can do this agitation. For example, you can have some volatile mold coating, which will generate a large amount of gas vigorously, and that will create a lot of agitation in the liquid metal, right? Then you can also subject the liquid metal to ultrasonication. In fact, this has become one of the popular techniques for grain refinement using the melting casting route. And it can also be done through physical or mechanical stirrer. You physically stir the melt by using a mechanical stirrer. You immerse the stirrer and agitate it vigorously. That can also break down the dendrites, and similar kind of stirring can be also generated by an electromagnetic stirrer. And you can also do gas purging, that will again lead to creation of bubbles into the melt, and it will actually stir the liquid metal, and that can also create enough agitation into the melt to break down the dendrites for them to act as the nucleation sites. Okay, so this is another way of providing additional nucleation sites as the melt is cooled down during the solidification process. Okay. So to summarize, we can say that there are two types of nucleation: homogeneous and heterogeneous. Homogeneous nucleation occurs uniformly across the parent phase without the aid of any surface or defects. Whereas heterogeneous nucleation occurs on a surface such as defect or mold walls, and for the nucleus to form, there is a critical free energy change or an energy barrier, and this energy barrier is much lower for the heterogeneous nucleation compared to the homogeneous nucleation, and therefore you can expect a higher nucleation rate for the heterogeneous nucleation, and that is what is being utilized for grain refinement by adding certain grain refiners which can provide a surface on which heterogeneous nucleation can take place. Okay, so that's the idea behind this melt inoculation, as we call it, in which a grain refiner in the form of some solid particles is added to the melt for them to act as the heterogeneous nucleation site and lead to a finer grain size in the solidified material. Okay, and I should also mention here that heterogeneous nucleation is more practical. This is what you generally encounter in practical scenarios, because as I said, the energy barrier for the nucleation is lower, and in every material you will have some defect to initiate the nucleation. And with that, we come to the end of this lecture, and the rest of the things that we have on this topic will be taken up in the next lecture. Thank you for your attention.